thing. So, okay. And I think we can start, right?
Yeah, why not? Yes.
There. Okay. So, apresentação. Okay. Oh, I have to. Yeah, it's better if I share, right? Okay. Are you seeing my screen?
Yes.
Okay. Okay. So what we are going to do today is first we are. Oh, I don't know what's happening. Okay, here. We are. Okay. Sorry, something weird is happening here. I don't know why.
Are you having what is the problem?
Okay. Because it was not staying where I wanted.
Oh.
So the first thing we are going to do is just review, just to remember what we have done last. You have seen last class. Then we are going to review briefly bifurcations in one dimension, saddle point, transcritical, bifurcation, pitchfork, and the inverse pitchfork. And we review also the workflow for drawing the nucline plots in 2 dimensions. Then we are going just to work a little bit with Fitzhugh-Nagumo equations for excitable state and for oscillatory state. And this is an important thing because Fitz-Nagumo equation for oscillatory state can be a kind of an archetype to understand when these equations will lead for an oscillatory state. And then we start to analysis of the bifurcation in Fitzhugh-Nagumo equation, because what you saw was in 1 dimension. Now that you see what's happening with Fitzhugh-Nagumo equations in 2 dimensions, and then you see what the stability of the fixed points has to do with the behaviors, then we do the analysis. The analysis in principle for more dimensions, it's more or less the same in the sense that you have to calculate the eigenvalues and eigenvectors of the Jacobian. But the difference, which is not a small one, is that the Jacobian, it's not going to be a 2-dimensional matrix, but it's going to be a high-dimensional matrix, and makes things less direct to calculate, right? But the idea of the bifurcation, this is what you should get, to understand. Because when you are going to apply this for any dimension, there are many details, but if you just work now, you are not going to remember them, and then you have to work them again. And if you have learned the idea, the concept of what you do in the theory of stability, then you can learn by yourself whatever detail you need. And so that's we are going to do. I'm not sure if we are going to do the exercise 0.3 or 0.5, maybe yes, maybe not. It depends on the time I get to do everything. And please, you just interrupt me and you can question everything, okay? So just remembering, if we have an equation, which is the time derivative of 1 dimension, so you have only 1 variable. If you have, you want to know how this variable is going to depend on time, you assume that it depends on only on the value that it has in that time. And then what you're going to have is a function of x that will tell you what happens to the evolution, right? This is how it evolves in time. If you want to analyze the linear stability, you have to first know that what is a fixed point. The fixed point is when f lambda is equal 0. So what you have to do, the first thing, is to discover the roots of the function f. So anytime f lambda crosses 0, the values of x, which is x star, and depends on lambda, because lambda is this parameter of the equation, that if you vary the parameter, you have different evolution, but you can understand what's going to happen to the fixed point, to the stability, depending whether you vary lambda. If f lambda of x is decreasing, in the sense just like, you see my, do you see my pointer here?
Yes.
Okay, good. So if lambda is decreasing in this point here, then x star is a stable fixed point. If the lambda is increasing, then you have an unstable fixed point. F lambda is tangent, sorry, I understood. If f lambda is tangent to the x-axis, then it touches 0, and you say that is marginally stable fixed point. Okay, so what happens to you see here you have trajectory, and then if you start in a given time, in a starting time, in a different value from the fixed point, the evolution is going to bring you to the stable fixed point. If you are in the unstable fixed point, it's going to stay there. It's going to flee from there. And if it's going to another stable fixed point. So you see that what happens to the value of x2, which is the unstable fixed point, is that it separates the region, the values of x, that will direct any point, any trajectory starting from a point above the unstable fixed point is going towards the stable one, x3, and or if it's below, it will evolve towards the x1. So it divides the basins of attraction of each stable fixed point here. Okay, here. Now, if you have a bifurcation, it means that you change the values of lambda, and by changing the values of lambda, you change the roots of lambda. And when you change the roots of lambda, or the behavior of the root of lambda, if it's increasing, decreasing, or whatever, then you are going to change the stability of the fixed point for that given value of lambda. If and only if the number or stability of fixed points for lambda a little smaller than lambda c differs from the stability of fixed points for lambda a little bigger than lambda c, then you say that you have a bifurcation, because what's going to happen at the value of lambda c, lambda critical, is that it's going to change the stability of the fixed points. Okay, so see here what you have many different f lambdas, one of which has a different value for a different value of lambda, and makes the points where f lambda crosses the axis in different points, so it's going to be fixed critical points. You see here that if you have changed it from here to here, you change it the value. You have changed the value of the fixed point, but you don't change the stability. if you have this tangent thing here, then if you increase a little bit more, there won't be any fixed point. If you go down, it is going to have two fixed points. And so what happens here is that it's the value of lambda for where the fixed point is just tangent there, it's a critical one. This is the idea. If you have one dimension, there is only 4 different types of bifurcation. You have something which is, there is no, for saddle node where you have something like that. Saddle because you see there is this thing that just tangentially margin touches the x-axis, and then from here there is no solution. From here, then you have 2 solutions. One will be one is stable when one is not stable. The transcritical or exchange of stability is because now the stability is going to be different or depending on the value of lambda. So for lambda equals 0 here, you have minus x2. Then the xdt, you have something that you have only one fixed point that is always, it's almost always 0 here. And if you go there, you have another fixed point, which is lambda, and the 0 fixed point turns into this unstable. If you have the supercritic or forward pitchfork, you see it's like a pitchfork. You have only one fixed point, and then you have 3 fixed points. And the stability of the 0 fixed point changes from stable to unstable. And the subcritical or inverse pitchfork is just the contrary. You have something which are 2 unstable here. You have the stable fixed point here that turns into an unstable fixed point. Okay, so I don't know where. Okay, so for a first order one variable ODE, only steady states and monotonic growth or decay are possible. So you don't have any periodic or chaotic solutions. So if you want to do something which is more interesting than just changing the stability of fixed points, you have to go to higher dimensions. I don't know why. Okay. Now, if you have something which you have 2 dimensions, what we have learned last class was the general procedures for nucleons. The nucleons are defined when, well, to begin with, we are going now to 2 dimensions. Then you have these 2-dimension things. And what we do to begin with is to define, to look at a fixed point, and then to write or to draw in the plot what are the lines where du, the tau is equal 0, or the nu, the tau are equal 0. So you have two different lines here. And you know that when you cross the u dti, this arrow, this crossing, should be perpendicular to the u-axis. And when you cross the nu d tau nucleon, you have this thing to be perpendicular to the ni axis. You see that it's not that it's going to be perpendicular to the nucleon, it's perpendicular to the axis that it corresponds. And Okay, then draw the label and nuclines, then lightly sketch bidirectional arrows each nucline, remembering that the arrow at UI nucline points perpendicular to the UI axis, and the VI nucline does the same. Then you take an easy point here to know, to discover if the dv d tau is greater or smaller than 0 for the two variables. And then you can see where it's pointing the arrow here. And you know that when you cross the V nucline, the component, the V component is going to change sign. So it's going to, it was going like that, but it was something up, then it has to go down. And the same for the U thing. Remember that when you move along the UI nucline, when you cross the UJ nucline, the direction of the arrow in the UJ direction across the UI nucline flips. This is the idea. It's better to look than to pay attention to all it's written here, just to look that, okay, you have to go up or down. Then you have quadrants, because you are in a two-dimensional thing. For each fixed point, you have two lines that crosses, the V nucline and the U nucline. Then you have four regions, and then you can write the things, right? The conditions, if they are greater or lower than 0. And you have to adjust the length of the arrows as the nuclines, then sketch the orbits. Okay, but you do, I mean, you can sketch the orbits here more or less, but you can do in your plots and your scripts that you have done already. Okay, and then you can do and see more or less what's happening to the flow. Okay. So the first practice that I'm not sure you have already done, what we are going to do is 8.1 and 8.2. We are going to get this equation, which is the Fitzhugh-Nagumo equations, with some values of the parameters. You have a parameter A, you have the parameter epsilon, Ni, and then you have a C and B. So we have all the four parameters here. And what we are going to do is, you see here, it's something that is crossing like that. And when we are going to change such that it's going to cross in the other side, I mean, it's going to be up, and here is coming down. So to see what's going to happen. This Fitzhugh-Nagumo equation is used to model the state, the dynamic state of a neuron when it's spiking or resting. And this is the normal resting state of a neuron if you have these parameters. Okay, then plot time series and flows numerical along with the new clients. Why is the result interesting and useful? I think we have done, right, Pedro, Cenk? We have done this last class, right?
Yes, we have done it.
Okay, so what we are going to do, I'm just remembering what's happening, is that here you have the nuclines, and then you have draw all the flow here, the direction of the flows here. And then when you do in more detail, okay, I don't know what I did. Okay, then you have something like this, because you do with a script, okay? And if you sketch the orbits that we have already done, okay, you have this one. You see that if you start from any place here, you are going here, and then it go up or down, but it ends up here. Oh, I'm sorry. But it ends up finishing in the fixed point, right? So everything is going to do this, and then you have only one stable point. This is interesting because when you look to the U and time here, you see that, you see if you start with a slightly different values of U, of positive V here, you can either go up or you can go down and then you come back. But you always come back to the same fixed point, and this could be something that is representing a spiking neuron. Okay, so, and this is exactly what happens to the neuron. There is a spike of positive U and then a negative U, which would represent the potential difference that you see across the membrane of a neuron. And then it's going to be, so it's interesting, but then, I mean, you have to have a stimulus to make it to go that way. You have to put some different values of V naught, right, to make it just go there. Okay, so the second practice, okay, here you have V. You see that with V it happens more or less the same thing, but in a different scale. Okay. The exercise 8.2, we have already, I mean, you have done it as well, right? James said to do this, but I think we have already done the last class. And you have a different value of C here. It's different from the other one where C was 0. Now C is small, but 0.1. And what happens to the nucline is that it's going to be here and not here, right? So it's going to be unstable fixed point. And because it's an unstable fixed point, if you start there, it doesn't stay there. I mean, a small perturbation is going to make him to go away from there. But it's not that it's going to diverge. They are going to be, they can be, I mean, there are situations that it can diverge, but in this case, they are not going to diverge, they are going to a limit cycle, which means that it's going to be in an orbit that is repeated every some period of time, and it describes a very interesting way of trajectory. So again, you do the same thing. You draw you try to discover more or less how the flow arrows and the nucline regions, and calculate the orbits and the time series. You use the equations. You use the algorithm you have done. Okay. Okay, so this is the idea, is to see that they are very different here and here, right? Again, it's the same thing. Look carefully, I mean, what's happening here and what's happening here. It's not, this is going to be an unstable fixed point. Okay, if you use your script and do all the flows, and then you're going to have something like this. What happens is that if you start from here, for example, it will go here, and it will go there, and there, and there, and it won't, I'm sorry. It won't go back. You see, that line here is not terminating, not ending in the fixed point. It's just circulating the fixed point. So depending on where you start, you have something which is periodic. So you're going to have a periodic orbit. And this is what makes the fixed Hughes-Nagumo equations so interesting, because you can change this. And instead of having something that will go up, go down, and then stabilize in a fixed point, it starts again to circulate around the fixed point and present an oscillatory results. Okay. This is a very interesting result. You know, I think I keep saying that, well, maybe Pedro has already listened to this, but there are a few equations or behaviors that you use to model whatever you want, right? So if you see something that is in equilibrium and just oscillating around the equilibrium, you know what you do. You just put many harmonic oscillators and put some noise, and then you are going to have the behavior you want. If you want something that is, I don't know, diffusive, you know what you do. You do something which is related to diffusion equation. So the Fitz-Nagumo equation is an oscillator with very peculiar properties and serves as an archetype to choose when you want to model a behavior that you see in a system that you want to model. Whatever. I mean, this is the equations that you should know how it behaves in order to be used when you need them, when you need a tool to model a specific behavior. So it's not only understanding the neuron, it's understanding the kind of behavior you're seeing in the. I bet you, it's not only the neurons that behave like that. Any question? You have already done also, Jen, this exercise, right?
Mm-hmm. I think, yeah.
You wanna do it again? Just to get it, or you are okay? You know, better go ahead.
I think we better go ahead.
Okay. Okay, so the idea now is how we generalize these ideas to understand how we deal with higher dimensional dynamics and stability. So what we know about the fixed point is that at the fixed point, now we have a vectorial equation here. So this function here will be a vectorial one, right? That may depend in a set of parameters, right? And what you know is that at the fixed points, this Fn is going to be 0. So the roots of Fn, when it's going to be 0, but 0, it must be 0 in all its components, right? Because you cannot have that, you know, you could have that n1, it's going to be there because dn1 dt is 0, but then n2 is not going to be 0, the derivative for n2 is not 0, then it's going to go away in the direction of n2, not in the direction of n1, but it's going to go away, so it's not a fixed point. So the first thing is that the fixed point is going to happen only if the vectorial, I mean, I would draw an arrow over the 0 as well to know to say that this is the vectorial 0. N star is a stable fixed point. If for any initial n not near n star, then nt returns to n star. So what you want is an attraction. You are going to have some points surrounding n star. And if you begin from any point in this neighborhood, then the evolution is going to bring the system towards the fixed point n star. Then you say it's stable. So the idea is you're going to, I mean, now, how do I do this? How do I do the mathematics of this? What I do is just to consider that n naught is different from n star and the difference is a vector, any vector, epsilon, which has a small magnitude or it has a controlled magnitude. The maximum value of epsilon that you can have, and is still all the trajectories inside that ball with that magnitude of epsilon will bring the system back to the fixed point. All of these points will be the basin of attraction of that fixed point, and it will give you a measure of the size of the basin of attraction, right? And if you understand that, you see that if this maximum value of epsilon tends to 0, then the stability of this fixed point is going to change, because if there is no point, because the magnitude of epsilon is equal to 0, that means that no point around at a star is going to return to the fixed point, and then it's unstable. But then, and this is the way of saying formally this, okay? A fixed point n star is stable if there exists a value of epsilon larger than 0, such that for n vector that belongs to the neighborhood of around n star that is less than epsilon, then the limit of the tending to infinity of this trajectory of this starting point is going to be the fixed point. If it doesn't happen, then you have an n star that is unstable. So we need to evaluate what happens to the length of an arbitrary perturbation, epsilon, under the dynamics that we are considering, which is given by the vectorial function f, right? So we are going to see what's going to see. Now you see that n naught starts here, but the size, the length of this perturbation, of this perturbation in time is decreasing, even if t is changing direction. Okay, but the main thing is that there is a value of action that is going to return there. So suppose we have the fixed point, and then we need the length, the magnitude, the modulus of this epsilon, this perturbation, which is the difference between where the system is and where the fixed point is. Okay, and we want it to decrease in time for all epsilon star. It's not that you cannot have a trajectory that you start in a point and then sometimes it decreases and then decreases again. Then you just take a neighborhood that is smaller than that. The important point is that in this rounding, if you are close enough of the fixed point, what's going to happen is that the modulus of epsilon is always going to decrease. And the problem is that both f is going to change, of course, and it's going to change and rotates this perturbation thing, right? So what you do, because you were what are, I mean, suppose you are in a, if you are in a, if you are in a two-dimensional system, it could be the value of x and y. But if you are in a higher dimensional system, that it can be very, very tricky. So what you do is just you do something which is, I think it's very beautiful. I mean, it's really interesting. What you do is, suppose you have the NDT at this point, which is near the fixed point. So you have this, the value of this evolution is going to be determined by the value of the vectorial function f at that point. And then the NDT is equal d, because n is going these two values, right? So now this is 0 because the fixed point does not change in time. So we are going to only have the perturbation, right? But this thing is going to be this equation here. So the evolution of the perturbation is going to be given by the function f as well. Then you have the NDT is the epsilon dt, as we have done, and then you have again, this is the value of epsilon, but we are considering very near, very small perturbations around the fixed point. So if epsilon is small, I can Taylor expand the function f around the fixed point, right? And this is the way you do the Taylor expansion, which is a little bit awkward, but you can see here is because you are always taking the scalar product with the divergent of m here, and if you are going to behave to be only in the if you're going to be only at a very near the fixed point for small values of epsilon, of the length of epsilon, what we can do is just to expand this. And when you expand this, you see this is a divergence, so it's a derivative. It will give you an operator which has all the derivatives. And what you can have, I mean, you can translate this in first order. Here is the epsilon here. Okay, this is the result of making all these equations for m equal 1. And then you have the Jacobian, which means that you are taking the first component of f and deriving against n1 and df1 to dnn, and then you do all the Jacobian thing that I'm sure you know. I'm assuming you know, of course. And what happened, I mean, if you don't know, just ask. When you do this thing, you have generalized for any dimension. The only thing is if the dimension is large, to calculate the determinant sometimes is not very, I mean, it's long and cumbersome and everything. But for 2 or 3, it's okay. So in higher dimensions, you have something like that. And you see that now I have a linear equation for C, for the evolution. This is 0 because it's a fixed point. Then you have something which is dx dt will depend on the Jacobian at the fixed point. So it may be not very easy if the dimension is very high, not very easy to calculate, but it's a constant. It does not depend on x. In epsilon, it does not depend on t. So you can work like that, right? So this is what you have. But this is a matrix. right? This is a matrix. So what's the exponential of a matrix mean? I mean, this is a symbolic way to write something, right? And this way that it's right is to say that the definition of the size of this thing, okay, the modulus of this thing is going to be epsilon. I mean, you expand this. So in the first term, you don't have any j of f being applied over on epsilon naught. And here you have one j of f applied to epsilon naught. And then you have a squared of it and a cubic form. And this is what means, because I can understand what is a square of a matrix. I cannot understand what is an explanation of a matrix, but then you use this way of writing, and then you can understand what is an explanation of a matrix. And how do I know now? If this thing is here, you see you have epsilon of t is this exponential, and applied over epsilon naught. How do I know if this thing, because I want to know if the modulus of this, which is the modulus, the size of the perturbation at time t, right? So we started with epsilon being epsilon naught, and then as time goes on, you just apply this operation, you're going to have this value of epsilon, the perturbation at time t, and you can calculate the modulus. And what I want to know if they are stable or not, if it is to know if this thing is growing in time or it's decreasing in time. And how can I do this, right? Well, then you have eigenvalues and eigenvectors that I assume you know, Jen, because you have a physics background, right? And then you had to have lots of quantum mechanics. So you know what eigenvalues and eigenvectors are. I assume correctly, I suppose. Jen? Oh, I don't know what you answered. Jen?
Yeah,
Okay.
I'm trying to understand the equations.
Yeah, but do you remember what eigenvalues and eigenvectors are?
Sorry, what's that?
You remember what is eigenvalues and eigenvectors?
Oh, yes, of course, yes.
Of course. Okay. So what we are going to do is just to take this matrix and find its eigenvalues and eigenvectors. And we are going to write it in terms of its so once I know which are the eigenvectors of this matrix J, I can write epsilon naught as a linear combination of its eigenvalues, because I'm going to decompose, to expand epsilon naught as a sum of the eigenvectors of J. And then when I'm going to do this J over epsilon naught, I'm going to be J over the first component, the first eigenvalue, and the second eigenvalues, and the third eigenvalues, and I can solve and decide and determine whether this is increasing or decreasing, right? This is the idea. If I have to take the Jacobian and apply over epsilon naught, then what I do, I find the eigenvalues and eigenvectors of J, and then I expand epsilon naught as a linear combination as an expansion in the eigenvectors, right? And then I can apply to each eigenvector the J, which is much easier because then I'll be applying the eigenvector, right? So that's what we are going to talk, just have a linear algebra review of eigenvalues and eigenvectors. I will go a little bit faster because you already understand, but if you haven't, please tell me. It's very important that you learn this. This is a powerful technique. Not only for this equation, but for any dynamic equation that you can have. So, for any well-behaved square matrix M, okay, well-behavior is that, mathematicians can come up with very weird square matrix, but if it's the way we are used to, and of order n, there exists eigenvalues lambda I, and n corresponding is this, this is the order n of the matrix, so there are n eigenvalues, lambda I, and n corresponding to normalized linearly independent eigenvectors, E1, En, such that the modulus of each one is 1, and if I take the matrix M multiplied by its eigenvalue EI, then we have the eigenvalue lambda I applied on EI. That means that when I take one eigenvector and I apply the matrix there, what's going to happen to this the result is just I'm going to multiply the original, I'm going to multiply the original EI by lambda, and I'm not going to rotate it. I'm just going to change the modulus of the result. EI keeps having a modulus of E1, but the result is going to be lambda I. So what I do is just I multiply this by lambda. If I have an arbitrary vector, then I will also rotate it. And this can be a little bit, and this makes things more difficult to analyze what the Jacobian is going to do with the equation. So what I do is just first, I will write epsilon naught as a linear combination of the eigenvectors of the Jacobian in the former equation that I have. So this is an arbitrary vector, which would be epsilon naught. And this is what's going to happen to each one of the components of epsilon naught. And that will make things much easier. To find the eigenvalues and to find the eigenvectors, what we do first is that we assume there are these EI and EI here, okay? So I just take the former equation here, and then I put just lambda, this term, in this side of the equation. So I have this thing, which would be 0, which means the matrix M minus lambda I multiplied by the identity matrix EI is going to be 0, which means that the determinant of this thing is going to be 0. Okay, this is a consequence of this. And then what I do is just to calculate the determinant of M minus lambda I, right? I suppose I know what is the matrix M. And then when I calculate this thing, what I'm going to do, what I'm going to have is n equations that I should solve to find the lambda i's. So finding the eigenvectors of M is then a problem of finding the roots of a determinant equation, which is a polynomial of order n. And if it's order 2, it's okay. If it's order 3, we can solve. And well, we can solve any polynomial equation if we have enough time or a good program, right? Finding the eigenvectors is a bit more involved, but we don't need to evaluate them at the moment. We just need them to exist. So remembering that now I have mi, I can calculate once I have the lambda i's, I can come back here with this equation here, and then I have again a solution for there are n solutions for each value of lambda I. There are a set of n algebraic equations for each one of lambda I, and if I solve it, then I can find what are the eigenvectors. But suppose you know what is this. It's the equation of it, right? So it's here. Okay? And now we have a theorem. If all eigenvalues of lambda I or a matrix are different, then there are n distinct linearly independent eigenvectors. You see that here I'm saying they are linearly independent, not they are orthogonal. They are orthogonal. You can, you can be sure they are orthogonal if M is symmetrical. Otherwise, you can only guarantee that they are linearly independent. And we can write any vector epsilon as the sum of multiples of the eigenvectors of M, a linear combination of them. And if the matrix M is symmetric, then the eigenvectors are orthogonal, and writing this is even easier. So we can expand our perturbation vectors in terms of the eigenvectors of the matrix M. So you can have epsilon is equal something like that. So it's a linear combination of it. Okay. James here says he has drawn the eigenvectors here as orthogonal, but they are not necessarily orthogonal. They are necessarily orthogonal only if M is symmetrical. Then, if I have the matrix over epsilon like that, I can write to put M inside the sum here, right? And then when I calculate here, you see, and then we have lambda I, EI, and now these are only numbers. They are not matrices anymore. Okay. I'm sorry. So let's go back to E to M EI, which you remember we have this epsilon naught for the equation when we started looking at eigenvalues and eigenvectors. We had this problem that is the Jacobian times T that you have to put there in the equation. So let's continue with the notation of M here, but remember we want to solve this Jacobian equation where instead of M we had the Jacobian of the problem that we have. Okay. Then when I have this thing, I will have all this matrix like that, right? Applied over M. Then remember that M applied to EI gives you lambda I, EI, like that. So if you apply another time, you have a lambda squared, EI, and if you apply L times, then you have lambda I to L to the exponent L EI. So when you have something like that, instead of having M here, you see, I have 1 here, right? So E, it's the identity, and then you have all these things here. Then you can write Yeah, because the identity applied to EI is identity, right? And then you have the identity should be written in everything here. But when you have EM applied to EI, you have E to lambda I EI, like that. But you can do this only because the vector that you are applying this matrix E to n is eigenvector of n. If not, I would have also I mean, you cannot reduce it not being a matrix. Here you have something like that, okay? Which means that this is really, really interesting thing for our purposes. So if I have this epsilon is AI epsilon AI EI, and if I apply, I'll have now. You see, if you apply in this epsilon is not an eigenvalue anymore because you have a linear combination of the eigenvalues. And then when you apply the m here, you have a sum that is going to be like that, right? Because here you have e to lambda I, and then you have e. Now, suppose now that we go back to our linear stability in higher dimensions, right? So we now write our perturbation vectors in terms of our eigenvectors. Which are our eigenvectors? The eigenvectors of the determinant of the Jacobian, right? So we are going to have here EI, right? And then remember the EM is going to be like that. Apply the results for our original equations, which were T times the Jacobian of the vectorial function f. Then what you have is something like that. Now look at here. Suppose you have, all the values of these lambda, our eigenvalues here. You know what they are, right? If they are positive, then this thing is going to go to infinity, which means that the size, I mean, if you have a vector that has one component that goes to infinity, it's the size, the modulus of the vector is going to infinity as well. And if you have many of them, then you are going to have many parts of it that's going to be infinite, and then it's going to infinity. If on the other way, if all of them are less than 0, then if you take the limit of time going to infinity, all of these components of the coefficients of the eigenvectors are going to 0, and it means that the vector, the perturbation, the difference from the point in the trajectory that you are and the fixed point is going to be 0. So what means is that the trajectory is tending towards the fixed point. Okay, so remember that lambda I are the eigenvectors of the Jacobian matrix J. But clearly, if all I, lambda I less than 0, then for all I, the thing is going to be 0, and the limit of the limit of the perturbation is going to be 0 as 10 tends towards infinite. However, if at least one of them is greater than 0, then it's going to infinity. Even if it's only one of 300 of them. In that direction, in the direction of that eigenvalue, the size of the perturbation is going to be infinity, and you have an unstable fixed point. So you see that we never assume that these EIs or the number of equations are two dimensions. We did in terms of the eigenvectors and eigenvalues, and all this demonstration is valid for any number of dimensions. So you have done something which is independent of the number of dimensions. So a lemma. Consequence is that if n star is a fixed point of the ndt equal to the vectorial function fn, then if the trace of the Jacobian matrix jfn is now we would need some extra square brackets there. If the Jacobian matrix is positive, then the fixed point of n star of n star is linearly unstable. Now, what he's saying that is not only you can look at the Jacobian matrix and calculate all the trajectories that you're going to be if you are near enough if you are near the Fn star, the fixed point, right? You see that if the trace of the matrix is left unchanged by diagonalization. So if I have, for a matrix M, any1, if I just diagonalize, if I rotate the matrix, the trace does not change. So if I take any unitary matrix here and I make this rotation here, right, which is q minus 1 and q equal lambda, then you have something like that, and was not diagonal, but if I can find which is this matrix Q that is going to diagonalize your matrix to lambda, capital lambda, then you have this thing. And you know that the trace of M is equal to the trace of lambda because you really diagonalize the thing is not going to change the trace. And then you have something that trace of M larger than 0, then trace of lambda is larger than 0. And trace of lambda is larger than 0, exists at least one j, which lambda j is larger than 0, right? You see, I'm not saying that if trace of lambda is negative, it means that there is not a lambda j which is larger than 0. What I'm saying is that if trace of lambda is positive, at least one lambda j is positive. And if one lambda j is positive, if I put it here, if I put it here, that component of the perturbation that we started, then that perturbation is going to be infinite, which means that one component at least of the perturbation is going to be infinite, which means that the point is unstable. Okay, so if you have then if n is a fixed point of n, then the trace of the Jacobian matrix is positive. The fixed point of n of f, n star of f of n star is linearly unstable, right? Suppose that our epsilon naught is aj. I mean, it's exactly in the direction of one eigenvalue. Suppose the aj is different from 0, then epsilon naught is going to be like that. It would be a sum over all the different eigenvalues, but now I assume that all other AIs, which means all other the coefficients of the initial state is 0, then just to write in one of them, then this J is up, not down, right? And then you have here is J, no, is J is lambda J is small, is not a capital J. And then you have something like that, but EJ is equal 1, so epsilon T is going to be like this, and so if lambda J is positive, which increases to infinity as T increases, so N star is linearly unstable. Okay. Now we can make a summary of the results. In n dimensions, if n star is a fixed point of this dynamic thing, then if the Jacobian of the matrix J of F, right, has n distinct eigenvalues lambda I, and then the fixed point is linearly stable if and only if the real part of all the eigenvalues are less than 0 for all lambda I. The fixed point is linearly unstable if one of them is larger than 0. And the fixed point is marginally stable if and only if the real part of the all eigenvalues are less than 0, less or equal than 0 for all lambda E, and at least one is equal 0. You remember, here is less than 0. Here you have less or equal. If one of them is equal 0, it means that it's going to keep its distance from the fixed point, and it's not going to tend towards it, depending on the initial condition that we have. Here you have the okay. Here you have the proof of it. You write the modulus of it, so you modulus of the expansion, and here you have already assumed that realize that the exponential e to t times the Jacobian matrix of the system is going to be. I can put the eigenvalues here, and then here I just write like that because this is the way you can write. This is the scalar product between EI and EI. Remember, I have all I's are different, so I have I and J here, so I have the thing, then I have something like this, I just put like that, and then I have the EI's scalar EJ. Observe that if the Jacobian is asymmetric, then the eigenvectors would be orthogonal, and I could eliminate one of their sums. But if they are not, if the Jacobian is not symmetric, then I cannot be sure of that. If real of lambda I are less than 0 for all lambda i's, then the sum of them are also negatives, and then all the limit goes to infinity is going to be equal 0. So the limit of epsilon, the modulus of the perturbation is going to be 0 at t tending to infinity, and the fixed point will be linearly stable. The fixed point is linearly stable if at least one of lambda I for any lambda I. In how you do, you start from that part, and you see that for real of lambda J larger than 0, and then you start from that point. don't make things less complicated, because the linearly unstable, the instability refers to all directions. So put in the least convenient or the most convenient direction that is going to flee away from this, flee away from the fixed point. Then you have something like this. Then he put it like this because you assume that all the AIs are equal 0 with exception with AJ. So, and then you have something like this, and then it's going to be infinity, and it goes to infinity. There is some trajectories for which the fixed point is going to diverge. It's going to flee away from the trajectory is going to flee away from the fixed point, and it means that the fixed point is linearly unstable. And the marginally stable is if and only if all the real things are different from 0, are less than 0 for all lambda j's, and at least one is going to be 0. So you just so if lambda I, lambda j are equal 0, then the real of lambda I, lambda j is equal 0, then the modulus of it is going to be 1. If one of them is less than 0 and the other is 0, then real is less than 0 and this guy is going to be 0. And here again, so you take all the probability, both are 0, one is 0, the other is less than 0, both are less than 0, right? And then summing over all j pairs for which ij pairs for which run over 0, and then you have a constant, and the fixed point is marginally stable because in that directions that you are that direction associated with the eigenvectors with null eigenvalues, then they are going to stay that distance from the fixed point. So it's marginally stable. Instability in 2 dimension, you can then study it. You have both eigenvalues positive, so both direction is going to flee away from the fixed point. It's unstable. If one eigenvalue is positive and one is negative, then this guy, the direction where the eigenvalue is negative is going to go towards the fixed point, but the other two is going to flee away. So it's unstable. Even if it goes there, then it's going to flee away. And both eigenvalues are negative, then everything is going to tend to the fixed point, and it's going to be a stable one. Now, this is how you find eigenvalues and eigenvectors for a large matrix. Is best left to Mathematica, yes, or a numerical solver. Yeah, okay. So, yeah, it can be a hard work, yeah. Lots of making counts, and there is no way to do this. I mean, you do it numerically. But for 2 dimensions, they are very simple. What you do is for a 2 dimensions matrix, you have A, B, C, D, then the determinant is just AD minus BC. The trace is A plus T, and the eigenvalue, the determinant of M minus lambda I equals 0, just give you the trace of M plus or minus the trace squared of m minus 4 the determinant of m divided by 2. This is, I mean, you can make the calculations and you see that's going to do that, but this is really a shortcut if you just use this formula. Because it's very easy, you know, to calculate both determinants and traces. And then to put the number here is just easy and right and fast. What happens if, okay, there is a problem if the eigenvectors are or not degenerate, in the sense that are they different or are they not? If they are different, and that means that this thing is different from 0, right? Then you have E lambda minus E plus plus E minus minus, because you have plus or minus here, right? So we are going to say lambda, the solution with a positive sign and the solution with a negative sign. If b different from 0, the b is the, you know, this part here of the determinant. So if b is equal to 0, what you say is that E plus minus is sigma plus minus. Here, you are going just to make all these calculations. I don't know if I should read it. I get but the point is, you find k plus minus here, right? It's just making the calculation. Then you can find k plus minus as a function of is a function of the eigen values and the components of the Jacobian of the matrix. And now you have to write this, and there is an over-determination, and okay, review of eigenvector. I mean, you have to solve this equation here, right? And then you have this E plus minus will be something which is a factor of normalization, and 2 values of B and K plus minus that you can calculate in terms of the components of the matrix. But it's not the only way of solving this, right? If you have these things, you just put there, and you have 2 equations. You know, when you have these and these, you have 2 equations or 4 equations for any component of this and you just have it. Okay. Then which is just our eigenvalue equation, so always true. And then you see, it just put it there. He assumed that, he puts it there, he finds this equation, which is lambda equal plus plus is equal. Here you have the trace, and here you have the determinant of the equation. So this is the eigenvalue equation, so always true, and then you have something like that. What are the eigenvalues? Again, you normalize because you want the modulus of everyone to be 1, and then you have something which is like this. I mean, this is, I leave for you, it's just mathematics, it's just algebra. I mean, it's just solving all the equations. I don't know if this is the best way, this is the way reading the equation is the best way to show you. Maybe you should only write by yourself, right? And see if you can separate the. It's simpler than that, really. So you have the eigenvalues, then you have the equations, and then you know, let me just see something here. I don't know if I ask you for you to go through these. Jen, we have time. Maybe you would like to do all these calculations by yourself instead of me just reading for you, right? What do you think?
I
You want to do you want to do this now so you don't have to do it at home?
I can do. I've done it like several years ago, like the eigenvalues and eigenvectors thing.
Okay, so
I
let's
don't think
do.
we need to practice this anymore. Although,
Okay.
yeah,
Okay.
although nowadays I prefer to solve these eigenvectors using computers, but
Yes. Yeah, I can understand that. Yeah, but do you understand how we do the solution, right?
yes, of course. It's like it's kind of basic for linear algebra.
Yes, that's it. So it's kind of basic, but it's a lot of small calculations that you can
Yes,
spend lots of time,
yes,
and I don't think this is the case,
yeah.
right? So let's go for the first thing.
Mm-hmm.
Okay, so the Routh-Hurwitz conditions. It's a general theory of stability for 2D ODEs. Okay, if a 2D system, then you have you have F and G, which are the two components of the dynamic function that determines the evolution of the system. Okay, and you have a fixed point at U star and V star. Okay, and this is the Jacobian matrix that if you calculate in the values of U star and V star, it will be the value at the fixed point. So this is calculated at the fixed point. Then what you have is that the lambdas plus minus is going to be the trace of the Jacobian matrix plus minus the square of the trace of Jacobian minus 4 the determinant of the Jacobian. The Routh-Hurwitz condition says that if the real of plus and minus is less than 0, and which is the same as the trace is less than 0, and determinant is larger than 0. Okay, you have something. And similar results hold in higher dimensions. There is an appendix in the Murray's book. And so that's what it says. Okay, if the real of is less than 0, then the trace is less than 0 and determinant is larger than 0. So you have the fixed point, and the trace of the Jacobian is going to be the sum, right? So we are saying that this thing is less than 0, the sum of this trace, right? And the determinant is this times this minus this times this. So this is going to be larger than 0. So the idea now is to apply this result to the Rosenzweig-MacArthur case, which is a model. Well, we are going to build a more realistic predator prey. This is an exercise. Let's build a more realistic predator prey model. Okay, it's the Rosenzweig-MacArthur model. I assume prey N by itself obeys the logistic equation. Assume the predator rate per predator P is Sn 1 minus SHn, where S is the predator search effort and H is the fraction of time taken to consume prey during which time predator cannot hunt. Okay? So this is S search effort, so it makes an effort and is going to, the rate, the probability that the predator, each predator is going to take one prey. Then you have Sn over the time that is available to predate. Okay, so the entity, which is the prey equation, is something which is the logistic equation, which has to do with the carry capacity of the ambient if there is no predator, right? It's going to, it cannot multiply as it wish because it depends on the environment. And then if you have the prey, if P is different from 0, then it will decrease also because the predator is going to be there, right? And so it depends on the thing. So this is the equation. And for the predator is going to increase the number of predators depending on how much it can eat, right? So, so EB, the efficiency of converting prey into new predators, because this is what happens if you eat something, you're going to have, I mean, if the predator eats some prey, it's going to be able to reproduce, then it's going to increase the size of its population, and the death rate of predators, because predators cannot live forever. So what you have here is the amount of new predators that enter the system, which depends on the number of prey that these predators can catch, and minus the predators that have died because they die. So so this is both equations. So you have a two-dimensional thing. These are the F and G, right? The dynamic equation for F and G. And this is the predator search effect. And the fraction of time that's consumed to prey during which time predator cannot hunt, the efficiency of converting prey into new predators, and the death rate. So the first thing you have to do is to make it dimensionless, right? Because you want equations that do not depend on dimension. So you have to define some natural units for n and p and time. Well, I think, okay. And how many parameters do you really have? Because when you make it non-dimensional, you know, like the wave equation, that you have some if you have the wave equation in the the only parameter that you have there is the velocity of the wave, right? And it's the only thing. Even if you have many things in the wave equation, I don't know, the nature of the nature of this system, the oscillators that you are having there, and lots of parameters, but then in the end, the wave equation has only the velocity of the wave equation, of the wave in respect to the medium. And so here you have to make it dimensionless in the sense what I can do. For example, I can respect here, but I'm going to divide anything by k, and then k I divide by k here, then I have divided by k here. So I have all this n over k here that don't have any, and then you have predators, then maybe you should divide, you have k, you have something like this, then you are going to redivide p over this s, h over k or times k, and then you can have something that will have only non-dimensional equation, non-dimensional functions here. And then there are some of these things that is going to be there. You cannot take it anymore, even in redefining these variables in these new units. Then these will be the number of independent parameters. Then you have to have fixed point, which means that this thing is going to be 0, this thing is going to be 0. Then find a condition to make the non-trivial fixed point exist and explain in words, which means that you have to calculate the Jacobian, and then if you have the Jacobian, you have to calculate the trace and the determinant of the Jacobian, and then you can use this Hurwitz condition, which is what they are saying here. And then you draw the nuke lines, then you sketch the orbits. Okay. So do you want to do this now, Jane?
I'm sorry, I don't have a pen and paper right now, but I can draw the node lines by programming.
Okay, okay. And the dimensionless is explained in the next one. You see, make dimension defines U and defines V, U and V. So you rewrite, then you have these equations here.
Mm-hmm.
So you have 1, 2, and B is equals 3 different parameters. Right?
Mm-hmm.
A, B, well, yeah. You don't have all of them. Then you have to fix points. So I'll wait you to do that. I don't know if you have this deck with you, Jen.
The what?
The slides, do you have it?
No, I don't have it. No.
Okay. So can you do this by looking at these two equations? I think you can, right?
Yes.
So, okay. Then I wait you to do. Pedro, I don't know if you are going to do this again or not.
No, I'm not.
We can go to the next slide, I think.
Okay. This one?
Yes. Okay. Do I need to draw the figures by myself or
Well, just to see if you did it. I mean, I can wait because we have time.
I don't have pen or papers.
Okay, then let's go. You understood everything.
Yeah, I understand.
But
Yes, it's
yeah,
just
but
solving
please
equations.
do, Jane, because this will help you to, fix all the content and how to proceed, right?
Yes.
Okay. You see that depending on the values of C less than 1 and C less than 1/2, you have different solutions. Okay, because you have different equations. And if you have now, if the real less than 0 and these guys are less than 0 and larger than 0, then you have this fixed point, and so you calculate dg, dv, you calculate it. Okay, you are here, you can calculate you can calculate the determinant, right? And this is the determinant that you have, because you have a dfu is going to be like this, df dv is going to be like this, and at fixed point, this guy is 0 and this guy is 0. So at fixed point, you're going to have dg dv is equal 0. So you can calculate the determinant, which means that dg dv is equal 0. This part is 0, so it's 0 here. You have just the multiplication of these two, the partial derivatives. Now, again, this is du d tau, dv d tau, and you have all these fixed points. So you have calculate this and putting dv is equal like this, then you have this fixed point. So df dv is going to have this point. The determinant is going to be this part times this part here, and since 1 plus bu squared, bu star is squared is larger than 0, we don't then a and b are larger than 0, and you calculate the sign of the determinant to know what happens. And because u star and v star are larger than 0, then it's going to be, the sign is going to be 1. It's going to be the determinant of J is going to be larger than 0. So the stability depends only on trace of J. Okay, so we are going to look at the trace of J, because if all the real are less than 0, which means it's a stable fixed point, we have to have these two conditions. And we have proved here that the determinant of J star calculated at the fixed point is larger than 0. So we have to look to the trace of the Jacobian calculated at the fixed point. Okay, here. At fixed point 1 minus u star is equal 0, then you calculate the trace of J, because I want to know if it's less than 0. If it's less than 0, then I will have a stable fixed point. Then you calculate this thing here. And again, you are looking at this part here. So A, B, and U star are larger than 0, then the sign of the thing is going to be stable. If P is less than 1 minus C and 1 over 1 plus C over 1 minus C. And then we are going to be stable with this thing. And remember, B is the predator search effort versus the fraction of time consuming prey versus the prey carrying capacity. Okay, so B is the predator is going to have an effort and the fraction of time that is consuming and the maximum the maximum number of prey that you have. So C is going to be death rate of predators versus predator search factor divided by the efficiency of converting prey to predators. If I increase the prey carrying capacity, it will tend to destabilize the fixed point, the paradox of enrichment, even if you have lots of it. So let's look at it. So there was a third case for FP, fixed point, which we missed before. Okay, which is the case? The case you have something like this and something like this that you have, and you can have a limit cycle. You see here, I have a limit. You see that this thing is spiraling away from the fixed point, and it's spiraling towards a limit circle. So I have a stable limit cycle around the unstable fixed point. We can use the ideas behind the Hurwitz condition, that this thing is less than 0 means these two conditions, to provide a general classification of 2D fixed point. Okay, so we want here a general classification, just as we had before, a classification for the one-dimensional thing. We are looking for the two-dimensional classification. It has, this thing has a fixed point at 0, 0. You can always move it back to arbitrary U star, V star. Okay, don't worry. I mean, we just put the fixed point at 0. The Jacobian matrix is just like this. Yeah, and here you have the calculation, the expression for the two eigenvalues. And then we are going to look for the fixed point at 0, 0, because we put the U star, V star at 0 to make the calculations or the things simpler. Okay, so all the eigenvalues are like this. So we have A, B, C, D. They are the 4 components of the Jacobian calculated at the fixed point. And from our analysis, is B different from 0? This we have already done before. You have P plus minus equal lambda minus B, and you have lambda minus plus or minus like this. This is P plus or minus. So I can have the expression for the two eigenvectors. Okay, so the idea is if I have a B and calculated everything, I just can take the expression of the P plus or minus that we had calculated there, and if you didn't calculate it, you just do it, Jen, at some point. Then we have this thing, right? Just and these are all the values of the eigenvalues, and of the depending on the eigenvalues, and here you have the eigenvectors. You have a stable node if you have trace less than 0 and determinant larger than 0. This is the Hurwitz condition. And if trace squared is larger then 4 times the determinant j of j, right? For example, if I have something like this, it could be -1, I don't know what's mean. This is the determinant, okay. And since the squared of the trace is larger than for determinant, both are real, and lambda plus is larger than lambda minus. You see, if this thing is larger than this is positive, both are real, and then you have trace plus something which is positive, then is larger than trace minus. And since trace j is less than 0, see if this is true. But if trace of j is less than 0, because you want them to be less than 0, you remember, because you want to be stable, then the trace should be less than 0, and the determinant is larger than 0. Then lambda plus minus are both less than 0, because trace of j is less than 0, and determinant is less than 0, because then you have a lambda minus minus is minus something which is less than trace. Then it will be negative. Either you put plus or you put minus here. And then both are less than 0. And if both are less than 0, I have a fixed point that is stable. Okay. Okay. This is a stable node. Now, if the initial condition is a linear combination of the two eigenvectors, then you have in time, this is the initial condition. Then the initial condition is going to evolve in time using this thing, because you have already expanded in the eigenvalues. Then, you know, if you apply the E to T determinant of the J, and the Jacobian of calculated at the fixed point, then you have the E lambda T, e aqui E lambda minus T, aqui E minus, E plus, you have the condition that is doing this. And our initial conditions convert to 0, 0, because both lambda plus and lambda minus are negative. And because lambda minus is less than lambda plus, but both are negative. So lambda minus has a modulus that is larger than lambda plus. And then it goes faster to 0. Then you have something that you have here, the blue direction is the direction of lambda minus. So something is coming here, and everything that is going here is going to, you know, it will be, because if you have something which is not in the direction of lambda minus is going, the component of lambda minus of E minus is going to disappear first. So we will be tending to the direction of E plus. And then, that's what's going to happen. It's going here, it's losing its E minus direct component, and then it goes to the E plus component, sorry. It goes to the E plus component, and then it converts like that. So this is what you have. This is a stable node, but the directions with, okay, if it's a stable node, both eigenvalues are less than 0. The directions, the eigenvectors that are associated with the larger modulus eigenvalue is going to disappear first, and then the thing is going to be left with the other, the slower modes of converging. This is an unstable node. So suppose that the trace of J star is larger than 0, and determinant is, you remember, this should be less than 0 to be astable. If this is larger than 0, then it will be unstable node. And I'm going to suppose that the square is larger than that. So what I'm going to say is that both lambda are 0. Excuse me, both lambda are real. So you have that real, you don't have a complex number here. And since the trace of the square of J is larger than this, right? This is larger than this, so this number, the square root of this thing, is going to be less than this number, right? Then lambda plus is going to be larger than lambda minus, and both are larger than 0. So if the lambda are larger than 0, the components of the initial perturbation that is associated with the direction of the first and the second eigenvalues are going to flee away from the fixed point. So the fixed point is really stable. You see here that everything is going away from the fixed point. Now, unstable node, right? So so you have the initial condition here, you have U and V here, which is the evolution of the thing. Our initial condition diverge from 0, 0 along E plus. And because lambda plus goes to infinity faster than lambda minus, that's the reason why they are going to infinity in this way, right? And du dt, dv dt, cu dv dv, and you have this at 0 you're going to have this Jacobian. Okay. This is just an example, right? But again, you have case 3. Now you have this thing less than 0, but you are going to have the other larger than 0. Just remembering the Hurwitz condition, you should have this less than 0 and determinant of larger than 0. So you have the case 2, this was positive, and this was positive as it should. Then you have this determinant is less than 0. But if this determinant is less than 0, what's going to have is that it's going to be a positive number here. Then both lambda are going to be real. And since trace of is less than 0, both are real, but now lambda plus is larger than lambda minus, and lambda minus is negative because this thing is larger than this thing, the square root. So the fixed point are, the fixed point are unstable because lambda plus is positive. And so you have something like this. It goes because of lambda plus goes to infinity and lambda minus goes to 0. Then you do something which is You see, in the direction of lambda minus, this thing is going to 0, and then it's go to infinity. And this go the direction, it's losing its direction in lambda plus, but then, oh, sorry. And then it goes to 0. The red line is the direction of the plusing, of course, because it's going to infinity, and the blue line is the direction of the minus, which is going here. Unstable direction, also called the unstable manifold. Stable direction, also called the stable manifold. Because why do you do this? Well, if it was only in two-dimensional problems, the direction and manifold would be the same thing. But what you want is that suppose you have many higher dimensional problem, then you'd have a collection of some of these lambda would be positive, and this direction associated, that is expand the subspace where all these directions are running away from the fixed point. And this subspace is going to be the unstable manifold, while the stable manifold is composed by the directions linked to the eigenvectors with eigenvalues that are less than 0. So, and you can have a spiral if you have the stable spiral. And if you have the trace less than 0 and the trace the square less than 4, the 4 times the determinant. And then what you have here is that you are going to have a complex number as this solution of this square root, right? And because you have this, the evolution is E2 is the exponential of this lambda t, right? If the lambda is is a complex number, then you have the real part and you have you have the complex part. In the complex part, we will something which is oscillatory, a sine or a cosine. And then you have something which is oscillatory. So, because you can have, the trace, you're assuming the trace of J is less than 0. And here, even if this thing is not real, the real part can be less than 0. And what is important to flee away from the fixed point is not if the lambda is real or not, but if it's the real part is less than 0. And the real part is this one. So if the trace of J is less than 0, then you have something which is less than 0, less than 0, and the real part is less than real. Then the magnitude of the perturbation from the fixed point is going to 0 as time goes to infinity. And this is what you are going to have. You see, you have something which is, what we are going to have is something that is circulating around the fixed point, but because this thing is less than 0, the magnitude of the thing is going to decrease as it approaches as time goes to infinity, and then it approaches the fixed point. And so this is an example of the stable spiral. It goes there. It's going to spin towards it's going towards the fixed point, although it spirals, it circulates around this system. Then you have unstable spiral. What's going to happen? Well, then the trace is going to be less, but the trace is going to be less than 0. So if the trace is less than 0, the trace. It's no, the trace is larger than 0, because if the trace is larger than 0, then both real is going to be, because the real part is this part, right? Because this one is going to be this one is going to be less than 0, and okay, trace square is less than this, then it's going to be the complex part, and trace is going to be 0. Okay, this is here. Trace of J is going to be larger than 0, then both real of lambda plus is going to be positive, and then they are going to spiral. This part is going to be, I mean, you have a real part that is going to increase the size of both components of both eigenvalues, and this part that is complex, it will be translated in sinus and cosinus, so it's going to oscillate around, but with a larger and larger and larger and larger modulus, which means it's going to spiral out and not to the fixed point. Because of this, the fixed point is unstable, it's an unstable spiral. And this, it seems to be the same thing, but it's going in this direction, right? It's not going like that, it's going like that. Okay. Now you have the trace is equal 0. If the trace is equal 0 and determinant is larger than 0, okay, this is okay. This is 0, this is 0, this is positive, so it turns to be negative. Then you have a complex thing that the real part, you see here, lambda plus or minus is just plus or minus the square root of determinant of I times the determinant of J star. And what's going to happen is that you are going to have stable oscillations around here, because you are not going to increase or decrease the size of the initial perturbation. So it's linearly stable neutrally, like Lotka-Volter. And here you have these circles or ellipses around this marginally stable fixed point. At the center, denote the structurally unstable to small terms with higher powers of U and V. This is the point, because if you have higher powers of U and V, then you can okay, just saying. Case is you have a center with higher order terms of trace of J. Now what I mean is here trace is 0 if you have the way we calculated thing and they have only these first order terms in U. But if you can calculate with more orders, because if it is 0, it is 0 in first order, but suppose that, well, if it's 0 in first order, I have to look to the higher order terms. So what happens if I have a higher order terms here, for example, the thing here? And then the fixed point happens to be if trace of J is equal to 0, then I have a linearly state. But if I have a trace squared, because I don't want to, trace squared is going to be 0, then I'm going to have this thing. But you could have something which is different here, you see. Because when I take square trace, then they are the higher, it should be a higher order for me to consider this part different from 0. And center with a non-linearity. Finally, the condition is something like this. Then you could have something which is always tending to this solution, then it goes and it never goes there if you start. And general classification of 2D fixed points. Okay, this is the case 7. You have a star, a stable star. You have minus than 0, and you have something which is equal. So you have 0 here, right? So it's always lambda plus and minus is just the trace of it. And because it is 0, it means that lambda plus is equal lambda minus. So everybody, in each point you have, it doesn't matter what is the composition of E plus and E minus that you have there, that both is going to tend towards the fixed point because they are positive in equal velocities, in equal rates. So what happens is that they are going to keep the direction they have. So they are going just like that. If we start here, then you go here always like that. You don't change okay, one of the direction is going faster than I suppose the red is going to be faster. I would have some curve like that. And the stable star is like this. Okay. Okay. And I can have the other way around. I could have something that makes the both are larger than 0. If both are larger than 0, we know it's going to be unstable because for the condition we are studying, for stability, you should have the trace of J star less than 0. But you have something which is larger than 0, then it will diverge. But it will diverge in the same velocity. So you are not, the trajectories that you have here won't make any curve. This is not the case of U and V independent, not structurally stable. And again, you have an example here. Then case 9. Then you have an improper node with the trace is less than 0, which would be okay, but the trace is equal to 0. So both guys are 0, are less than 0, then it's a stable thing. And if they are 0, they are equal. and then they have something like that. Okay. Stable improper node is just that you have all initial conditions convert to 0, 0 along E plus, because E lambda minus goes to 0 faster than E lambda plus. It's just taking all these. Oops. And then the improper node. And again, I mean, and then unstable star, and then the general classification. I mean, there are lots of to remember, but what the main thing is the trace of J star is going to define really if the real part of the lambdas are going to be less or minus or larger than 0, and that means that it's the component of the initial condition is going to increase or decrease, or the initial perturbation has two components, and the two components may increase or decrease from the difference from the fixed point. And you have, if you have one or two, that things are going away or not. And what happens if the determinant is less than 0, and you have unstable saddle, because one thing could be positive and the other could be negative. And because you remember, here, if you have something is positive here, if you have this plus this is going to be negative, it's going to be positive, but if you have this minus this, and this part is negative, then this is positive, then you have one positive, one negative, then you are going to have one that goes away, the other that doesn't go away. So you have the saddle point, stable or spiral. Again, you have to, the spiral, if you have the spiral, you have something which is, if you have the spiral, then you have something that is, there is a complex value for these eigenvalues. And if you have the trace equals 0 and determinant larger than 0, then you have a center. If you have a stable star because they are equal, then you have something that just go away, and no, just come into the fixed point, and unstable star if they go away. The unstable improper node is that when you have trace and equal. So you have the improper means that the lambdas are equal one to the other, and then you have to do something. I mean, you have to be careful in finding which are the because it's a degenerate eigenvalue, but I mean, it's not complicated. Okay, and if determinant less than 0, you have unstable state. So, okay, they are just repeating what I'm saying. Yeah. And then again, you are repeating, it's just to understand. I mean, this is interesting to do, because what you are doing here is what means what happens to the determinant, what happens if it's larger than 0 or less than 0. And then you can understand what's happening with that. It all depends if the real part is going to be positive or negative, and if there is a complex part. And then if that happens to one or for both, for one or both eigenvalues. And this is, I recommend that you really read with careful and understand. I mean, it is an exercise to, okay, it's a stable node, then I have to this, and this. Because, come on, really, there are 10 different stable points. It's much better to understand what each part is doing than really memorizing everything. Okay, so here you have data in trace array, right? And this is maybe a good way to see what's happening. It's just happening here. This figure is try to summarize everything. And this maybe a good exercise is just repeating by yourself this figure. So yeah, so this is what to do to classify the two-dimensional fixed point. And then you can calculate, you can reproduce all this figure here. Okay, I think I'm going to finish here, Jane, because I think we have covered a lot of the things. And I think we went maybe too fast. I'm not used to these kind of classes, but I'm going to stop by here.
Okay.
Any questions?
No questions.
So I really recommend you to reproduce this figure. Right, Angel?
Oh, yeah,
Jane.
it looks straightforward.
It's just a function of
Yeah.
yeah.
Yeah, and not reading, just reproducing, because when you do this, you are forced to rethink everything and then you understand.
Oh, okay.
Okay.
But can I have the slides?
Yeah, I think so. I mean, the slides are not mine, Jane, but what do you think, Pedro? James, it becomes available for the students as well, right?
Yes, there is a link to the drive. I can give you the link.
Oh,
if you-
great.
Okay. There are many. I don't know if the drive is that one. So you go to the end of because there are lots of years there. Okay. Put the one for this class. You find that it's lecture number 8, I think.
Okay.
And it has something October 2024, and maybe there is my name.
Okay.
Rita. Okay.
Mm.
Okay. Thank you then.
Thank
All
you.
right. I will finish the recording here and